Okay, good afternoon, everyone. Going to tackle the last two topics on our agenda, which is the node voltage and the mesh current analysis. Week of extra notice. These are the topics. These two are the topics that will also be on the final exam, in addition to the other circuit analysis techniques that we have learned. So we were talking about, we introduced the concept of nodes, branches, loops, and a mesh, and then we looked at node voltage analysis. Let's look at an example. And try to get through node voltage and then introduce mesh current today. We probably won't be able to get to the example for mesh current, but at least want to get through this one. All right, so circuit has 4 resistors and 2 current sources. And we are asked to solve for all the branch currents and the node voltages. So this should be node load voltages. I1 and I2 values are given to us, 10 milliamps and 50 milliamps, and resistor values are also given to us. So let's begin. First thing I'm going to do is I'm going to inspect the circuit and see if I can reduce any of these components. So to do that, let's count the number of nodes. How many nodes do you see in this circuit? 2, 3, 4, 5, 6. How many say 6? How many say 5? How many say 4? How many say 3? 2, 3. How many say none? Doubtful. As a rule, always check if you have 2 nodes, whether there's a wire between those 2 nodes. If there's a wire between those 2 nodes, then it's the exact same node. So if we say these are 2 different nodes and there's a wire between them, that means it's the exact same node. So there are in fact only 3 nodes in that circuit. So you got node on the left, node on the right, and node at the bottom. Let's call this A. Let's call this node B. Let's call this node C. And the ground symbol or the reference symbol is shown right here, but we are not held to that node. We can choose any node we want. But for the purposes of this analysis, I will go with what is given to us and choose node C as my reference. If node C is the reference, that means voltage VC is 0 volts. So right in the first step, we identify 3 nodes. If you have 3 nodes, that means we have 3 unknown variables to solve. We need at least 3 equations. Now, I chose one node as my reference. That means I automatically have an answer for one of those 3 nodes. Only need to solve for the other 2 nodes. That means I need only 2 equations to solve them. Okay. Also, what we can see here is that resistors R2 and R4 are in series. Are in parallel. My eyes are in worse shape. R2 and R3, sorry, not R4. R2 and R3 are in parallel, and I can reduce them before I begin. So let's combine and state it as R5. R5 is the combination of R2 and R3 in parallel, which is 2K in parallel with 1K, or 10K, sorry. And the answer for that is, of course, product of the 2 divided by the sum of the 2 comes out to be 1666.667 ohms. Right? We can reduce the number of resistors, thus we can reduce the number of equations. All right, now let's redraw the circuit. I'm going to make a larger circuit on the right and redraw this. So let's start with R5 first. R5 is at the top. I have the other two resistors, R1 and R4 to its right. I have a current source on the far left, and I have another current source far right. I1 is pointing up, I2 is pointing down. And then let's join the connections. So line. Okay. Excuse me. This is R1. This is R4. This is R5, which was the parallel combination of R2 and R3. Now, the next step in the setup of this problem is to assign branch currents. So let's take IR1, for instance. Which direction would you choose IR1 to flow? I think it's going up or going down? Up. How many of you say down? Some says up, some says down. The point is actually that it doesn't matter what we choose. We could choose it going up, we could choose it going down. For R5, we can choose it going to the left, we can choose it going to the right. It absolutely does not matter what direction we choose. This is an assumption on our part, but once we make this assumption, we have to stick with this assumption for the rest of the analysis. Okay, so let's say I choose IR1 going down. Okay, and then IR4 also I choose as going down. And IR5, let's choose this going from left to right. Now, once we've made this assumption, it follows that the branch current that we chose is going to cause a voltage drop. Now, this is important because we chose IR1 coming down from the top. That means the point of entry is at the top. So the voltage drop across R1 is plus at the top and minus at the bottom. And this is absolutely important. Okay, because when we write our equations, it will become, let's note this down, node A, node B, and node C at the bottom. It's absolutely essential. Everybody understands this. The point is, when we assume the direction of the branch current, it does not matter what direction we choose. It could be completely opposite to the laws of physics or the laws of circuit analysis, and you would still be fine. Okay. But once we choose our direction, as in this case, IR1 is coming down from the top, it means polarity of this voltage is plus at the top, minus at the bottom. And this would mean that when we write our equation, it would be VA minus VC. If we had flipped, if the current was actually going up, then plus would be at the bottom, minus at the top, and it would be VC minus VA. Let's take a pause, think over those statements. Let me know if you have questions. Does everybody understand the branch currents and the assumption? Okay. All right, so let's do the other three currents. IR5 entering from the left. So I would say VR5 is plus on the left and VR4 plus at the top. And that's it. That's the setup of our problem. We have I1 coming in from here, making a right turn, going there. And we have I2 coming on the far right. Now, all we need to do is apply KCL at both those nodes. So, apply KCL at node A. What do I have? I have I1 entering and IR1 and IR5 leaving. So I'm going to write I1 entering, so plus I1 minus IR1 minus IR5 is equal to 0. That's the first step, KCL. Then apply Ohm's law, VR1 over R1, VR5 over R5. After applying Ohm's law, I expressed each branch current in terms of the resistor voltage. Now, express each resistor voltage in terms of the node voltages. And VR1 is now VA minus VC. Similarly, R5 is connected between nodes A and B. Because currents going from left to right will be VA minus VB 0. Let's take a pause, look through these 3 steps, and let me know if you have any questions. First step, write the KCL using the branch currents. Second step, apply Ohm's law. Third step, express in terms of the node voltages. You follow these 3 steps, you can solve any circuit. And again, I'm letting you all know this is a topic that will be assessed on the final exam. So far, so good. Okay. All right, all that remains now is to plug in all the known values. All the known values means the resistor values, the current sources, the voltage sources, everything that we have. Plug in and generate our equation. So I1 is given to us as 10 milliamps. So 0.01 minus VA minus 0. VC is a reference node, so it automatically has a value of 0. R1 is 1K, so 1000. And VA minus VB divided by R5, which is 1666.667. 0. Now I want to reduce this and get it in the form of AX plus BY is equal to C. And so I'm going to take this equation, multiply it throughout by 1000. So I obtain 10 minus VA minus 0.5999 VA minus VB equals 0. Solving this, we finally get 1.5999 VA minus 0.599 VB equals 0. And you will note and label this as equation 1. Okay, that's our first equation. Two unknown variables. That means we need one more equation in order to solve for VA and VB. We're doing good on time, yes. All right, let me know if you have any questions. There are two, which two terms? Oh, yeah, that's true. It's 10. Thank you. Right? Okay. Now let's apply KCL at node B. And we obtain, what do we have? At node B, I have RI5 coming in, I have IR4 leaving, I have I2 also leaving. That means IR5 is positive, IR4 and I2 are negative. So IR5 minus IR4 minus I2 is equal to 0. That's the first step. Write the KCL expression in terms of the branch currents. Once you have the KCL expression, apply Ohm's law, and I can write V R5 divided by R5 minus V R4 divided by R4 minus my current source I2 is equal to 0. Once you have the resistor voltages, now express each resistor voltage in terms of the node voltages. And so I get VA minus VB over R5. And VR4 is connected between VB and VC. So VB minus VC over R4. And I will go ahead and take I2 on the right at this time. That's a constant. Plug in all the known values at this point. VA and VB are unknown, so that stays as they are. R5 is 1666.667. VC is 0, so VB minus 0 divided by R4. R4 is 2 kilo ohms, so 2000. And then this is 0.05, 50 milliamps, 0.05 amps. All right, I have 2000 in the denominator. So I'm going to multiply everything with 1000. That gives me 1.199 VA minus VB minus VB is equal to 100. consolidate all variables, and I get VP is equal to 100. And this is our I guess third time was the charm. All right, and this will be our equation 2. Two unknown variables, VA and VB. We have our two equations. You can solve these equations using any method you want. Solve it by hand, manually, manual calculations. Use your calculator, program a linear set of linear equations in there. Any method you want. Determinants, matrix, matrices. So let's note it down and let's go upstairs where we have more space on the left. So the equation 1 and 2 with any method. And what you will obtain is this. VA is equal to minus 13.569 volts. And VB is equal to minus 52.858 volts. Okay. Minus 13.569 and minus 52.858. Those are simply the values of nodes A and B with respect or with reference to node C. Anybody tried solving these equations right now? If anybody did you get the same values? You got the same values? Right, thank you. So let's talk about what these numbers mean. Remember that one-dimensional diagram where voltage is a height? So all this means is that if C is my reference, meaning it's at 0 level, and node A or point A is 13.57 volts below C level. So node C is here. This is 0 volts. Go underwater. And node A is 13.569 volts below C. Node B, however, is, and of course this is not to scale, is right here. And this is 52.858 volts below C. That's it. That's all it means. It doesn't mean anything else. Okay. If you chose, let's say, the beginning of the analysis, 30% of the class chooses node C as the reference. The other 30% of the class chooses node A as the reference, and the rest of the 40% of the class chooses node B as the reference. Your values for node voltages would be different, but your resistor voltages and your resistor currents would not change. Again, remember, node voltages are always with respect to a particular node in the circuit, right? The actual voltage between across a resistor and the actual current through a resistor will always turn out to be the same, no matter what you choose as your reference node. If you chose A as your reference, then A would be 0. So I'm going to write it down below, right here. If A is reference, then VA is 0 volts. VC would be plus 13.569 volts. And what would be VB? If A is my reference, what would be VB? 39 point. Sorry, this would be minus 39 point, what did you say? 289. Thank you. So with with C as my reference, node A is this value, node B is this value. But with A as my reference, VC and VB are completely different. But the difference between the 2 points, the voltage between those 2 points does not change. Does everybody see that? Let's take a pause, think over that. Let me know if you have any questions. Okay. For practice, I would strongly recommend you solve using A and then B as the reference node. You should arrive at the same resistor voltages, same resistor currents. We already know what the resistor voltages are, right? VR1 is VA minus VC. VR5 is VA minus VB. Since VC is my reference and it's 0, then VR1 is simply equal to VA. VB, of course, sorry, VR4 is across R4. VC is my reference is 0. So VR4 is equal to VB. That's the voltage. No matter what value you choose for your reference, this VR4, VR5, and VR1 will not change. You will always obtain the exact same values. And the current I, of course, is right here. IR5, IR4, and of course, you can also calculate IR2 and IR3 that way. And this is the way we can use node voltage analysis to solve for resistor voltages and resistor currents, which is what we learned by using Ohm's law, KVL, KCL. All right, questions? Did the steps make sense? Okay. There will be one more homework posted on node voltage and mesh current and a little bit of Thevenin. And next week, when we are done with our final quiz on Monday, which is on op amps, the rest of the time on Monday and then Wednesday, we will solve those example, the whole homework problems in class. So everybody can see, you practice beforehand and then you come to class and you can see how the solutions work out. Okay. All right, so that's node voltage. Let's go to mesh current analysis. Now in mesh current analysis, let's see. The first thing you have to understand is that mesh currents are completely different from branch currents. Branch currents are the actual currents that are flowing through the circuit branches. But mesh currents are not real. They are hypothetical. They are purely theoretical, simply for the purposes of analysis. So mesh currents are not real. Okay, and I'll explain why. You see, there are three meshes in this example, right? One, 2, and 3. And they're labeled I1, I2, I3. Normally, a branch current is drawn in parallel to a specific branch, meaning if you have a resistor, that current is parallel to that resistor, or any component for that matter. If you have a source, that current is in parallel to that source. But the mesh currents are drawn in sort of a loop. Okay. And then when you draw these mesh currents in a loop, you can see that if there is a resistor that is shared between two meshes, it also shares two mesh currents. And in this specific case, I1, let's look at I3, sorry, R3. Okay, so this is R3. And in R3, what do I have? I have I1 that is on the left side, and then you have I2 that is on the right side. And you see the current directions are completely the opposite, which is not possible in real life. Current flow results because of the difference in potential between 2 points, meaning one point or one end of the resistor must be higher than the other in order for current to flow through. Okay, if the left end is higher, then the current is flowing from left to right. If the right point is higher, then the current is flowing from right to left. So you cannot have two currents flowing in the same branch at the same time. It's physically impossible. Right? Am I making sense? Right? Branch current, for a current to exist in a resistor, one end of that resistor must be higher in potential than the other one. And then the current is flowing from high to low. So we cannot say I1 and I2 are flowing in the same resistor at the same time unless they are purely hypothetical. Okay. So again, mesh currents are distinct from branch currents. They are purely theoretical. They're completely, they're only used for the purposes of analysis, only to write equations. Okay. So that's the main thing. Now, the way we work with mesh currents is we apply KVL to generate our equations. Okay. So in node voltage analysis or nodal analysis, we are thinking in terms of nodes. That means currents are flowing in and out of those nodes, right? So we apply KCL to generate our equations. In mesh current analysis, we are going to apply KVL to generate our equations. So let's say this is mesh 1 on the far left. This is mesh 2 on the right, and this is mesh 3 above. M1, M2, and M3. Let's apply KVL to M1. So mesh 1, apply KVL. You sum up the voltages. I'm going to say minus VA plus VR2 plus VR3 is equal to 0. Or you could say VA minus VR2 minus VR3 equal to 0. Same equation. Okay. VA minus VR2 minus VR3 is equal to 0. Same equation, no difference. Now, VA, of course, is a source. I'll leave it as it is. Now we apply Ohm's law, V equals IR. And we are going to express each resistor voltage in terms of the mesh current. Okay, in terms of the mesh current. But now VR2 and VR3 are both shared. So that's R3. And this is R2. R2, you have I1 going in this direction. And you have I3 going in this direction. So now if there are two currents in that circuit, that means there are two hypothetical voltage drops. Excuse me. And these drops and have a polarity like this. Same thing here and same thing here, which again is impossible, right? On the left, we are saying that the top of R3 is higher than the bottom. On the right side, we are saying the bottom end of R3 is higher than the top, which is physically impossible at the same time. So when I write my equations, I'm going to write VR2. Now, how should we treat it? If I am applying in mesh 1 and I'm summing up the voltages, then VR2 will have two components. You have a voltage drop. Let's call this voltage drop VR2 due to I1. And this voltage drop would be VR2 due to I3. Again, these are hypothetical, not real. In R3, I can say this is VR3 due to the mesh current I2, and this is VR3 due to mesh current I1. Right? Two voltage drops. Okay, two voltage drops. Let's take a pause. Let me know if you have any questions. All right. So question being asked is whether the values of the voltages are the same. Magnitudes. So it's versus the sign. We don't really care about those right now because those are unknowns. We are only interested in writing the equations. So you're asking about the actual value for or the magnitude of the resistor voltages, right? Do you mean these values right here? Well, those are complete unknowns at this point. The answer is at the end, if it turns out I1 and I2 are the same, then it could be same, but it just depends on circuit variables. The actual answer, I mean, not the answer. The reality is that we don't know, and actually it does not matter. We are simply writing equations at this point. We will solve those equations at the end, and then we will know what the actual branch current is. Right now, we don't know what I1 is, we don't know what I2 is, we don't know what I3 is. So it does not matter. We're simply treating them as unknown variables, and we're going to write our equations, and then, well, at the end, we'll see what happens. Yes. The currents, the question being asked is the direction of the mesh currents. Does that matter? The answer, it does not. It does not. It only matters when we actually write the equations. Like right now, I have VR3 due to I1 and I2, and it causes a polarity, right? So when we write our KVL equations and we add them, we have to keep this in mind. So the assumption does not matter. No. So question being asked is, do they all have to be clockwise? The answer is no. They could all be clockwise, they could all be counterclockwise, or it could be a mix and match of directions. It absolutely does not matter. Yeah. So it absolutely does not matter. Okay. For now, let's write our equation. So VR2, as we were writing, could have two voltage drops. I'm going to say VR2 due to I1. And now it'll be VR2 due to I2. And if I treat both of these as two voltage drops, they both have the opposite sign because the current directions are opposite. So when I add them in KVL, one of them is added, the other one is subtracted. Okay. See, I'm applying KVL in this direction, right? In mesh 1. I have two voltage drops right here for R2. If I treat plus VR2 and I say minus VA, say then the voltage drop due to I1 is positive, voltage drop due to I2 is negative. Same thing with VR3. With VR3, I'm going to have VR3 due to I1 is positive, and VR3 due to I2 is negative. And that sums up to 0. And now we simply express each voltage drop in terms of the mesh current. And I can write minus VA plus I1 times R2 minus I2 times R2 plus I1 times R3 minus I2 times R3 is equal to 0. And I can consolidate this equation or consolidate the terms, and I can simplify this equation in this form. I can write I1 minus, oh, sorry, this is I3. Times R2 plus I1 minus I2 times R3 is equal to 0. Okay. If I chose the equation, like if this equation I write in this form, VA minus VR2 minus VR3 is equal to 0. Right? Simply summing up the voltages in the opposite direction. Instead of minus VA, I now have plus VA. So then everything is a voltage drop. VA minus VR2 minus VR3 equals 0. Same equation, but no difference. I'm simply summing up in the opposite direction. So then I would obtain VA minus VR2 due to I1 plus VR2 due to I3 minus VR3 due to I1 plus VR3 due to I2. It should all sum up to 0. Right? That 1 minute left. Does everybody see what I'm trying to show here? Right? You can write the equation in any direction. So it doesn't also reinforces the point that we made earlier that it does not matter what direction you choose for your mesh currents. Right now, one current, the two mesh currents are in the opposite direction. If we chose both currents going in the exact same direction, meaning one is clockwise, the other one is counterclockwise, and they're both going in the same direction, then in this mesh, when we add up the currents, they would both be positive. In mesh 2, they would turn out to be negative. Okay, so here I'm going to do mesh 2. We have about 40 seconds left. So if you have to leave, you can leave. I'm going to finish up mesh 2 and then I'll end class. So in mesh 2, when I apply KVL, before I finish this again, reminder, quiz on op-amp on Monday. You all have a homework. Try to get it done by Sunday night. If it takes until Monday night, that is fine. But if you try to get it done by Sunday night, you can have questions. You can ask me on Monday. All right. Okay, so for mesh 2, I'm directly going to write the shared mesh. So I have VR3 due to I2 minus VR3 due to I1 plus VB and plus VR4. R4 is not in a shared branch, so it only has one voltage drop, does not really matter. Then apply Ohm's law. I can write I2 times R3 minus I1 times R3 plus VB plus I2 times R4 is equal to 0. Consolidate the terms and I get I2 minus I1 times R3 plus I2 times R4 is equal to 0. Okay. Those are the equations we obtain. What I really want to point out is this. VR3 in mesh 1 is I1 minus I3. In mesh 2, the same voltage is I2 minus I1. And that is because of the current directions we chose. Okay. If both I1 and I2 were going the same direction, then in mesh 1, it would have been I1 plus I2. And in mesh 2, it would have been minus I1 minus I2. So the equations will eventually balance out. Okay. The equations will eventually balance out. So it does not matter what we choose as our current direction and how we sum up the voltages. Absolutely does not matter. All right. So we'll end class here today. Quiz on Monday, and then we'll look at the example for mesh current analysis after the quiz on Monday.